morning, dear students. Today I am going to discuss asymptotic notation, about asymptotic notation. In the last class we have discussed about introduction to the algorithms, what is the analysis of algorithms, what is algorithms, and what is design of algorithms, and where the algorithm is used, or the use of algorithm in your computer solving computer problem, and the way of solving the computer problem, and different steps of solving the computer problem. And in that case, algorithm is a vital role. Designing the algorithm is a vital role to solve any particular computer problem. And again also we have discussed how to analyze the algorithm. In that case we have discussed about a Turing machine model of analysis and RAM model of analysis, and also we have defined what is time complexity and space complexity. And today's class we will discuss about asymptotic notation. Now, order of growth. Now question is, what is asymptotic notation? What is asymptotic notation? Asymptotic notation is nothing but the behavior of the algorithm. Asymptotic notation is nothing but the behavior of algorithm for as the size of the input increases. Asymptotic notation is nothing but it is a notation where it explains the behavior of the algorithm as the size of the input increases. Suppose in case of a function, asymptotic notation of a function indicates what is the function growth of the function, how the function behaves as the size of the input increases for the large value of the input size. Now, in this case, we will discuss about order of growth. Order of growth means it is the how order of growth of a function means how the function grows as the function, how the function, a particular function grows as the function of its input. Hence, the order of an algorithm is the how the algorithm will grow as the size of the input. Now, hence order of an algorithm translates the efficiency of an algorithm. Order of an algorithm translates the efficiency of an algorithm. It is defined as the growth of an algorithm in the function of inputs, and hence it is qualitative measure of an algorithm's performance. Let us consider three examples here. In the first example, x is equal to x plus y. Y. In the second example, for I is equal to 1, I is equal to 1 to n, x is equal to x plus y. And the third example, for I is equal to 1 to n, for j is equal to 1 to n, x is equal to x plus y. See what is happening. In the first example A, the statement will be executed only once. It is independent of the value of n. But in the second example, the addition x is equal to x plus y happens how many times? N times, starting from 1 to n, and it depends n times. But in case of third example, the addition x plus is equal to x plus y happens how many times? N square times. N square times. Hence, as the input increases, as the value of n given, and that means in the first example A, the addition does not depend on the value of n. The second, it depends on the value of n, but in or linear in n. But in the third, it is the quadratic in n. Hence, what happens? If these three algorithms or the three codes are used in three different algorithms, and then what happens? The growth of the first one is constant, independent of n. The second one is the growth is order of n, but the growth of the third function is order of n square. Hence, from this example, we are clear that how the order of growth is nothing but it is how the function or algorithm grows as the input as the function of input. Now, in this case, we will define a notation called Bagwan notation. Bagwan notation. Actually, these notations give the order of growth, and how this order of growth is read by a particular function or bounded give upper bound for a particular function. Suppose there is a function fn whose order of growth we want to know, and how this function fn's order of growth is upperly bounded by another function. Say if fn is a function and gn is another function, we say fn is equal to big O of gn. We say fn is equal to big O of gn if and only if there exist two positive constants c and n0. There exist two positive constants c and n0 such that f of n, value of f of n, is less than or equal to c of value of g of n for all n greater than or equal to n0. That means we say fn is equal to big O of gn. Fn is equal to big O of gn. That means fn is equal to big O of gn if and only if there exist two positive constants c and n0 such that f of n value is less than or equal to c into g of n value for all n greater than or equal to n0. That means you see in the figure, illustrating the figure, there is the curve for c of gn and there is the curve for fn. Now at a particular value n0, beyond that the value of fn is always less than or equal to the value of c of gn. If this is happening, we will say fn is equal to big O of gn, and in that case we will say that gn provides an upper bound. Gn provides an upper bound to the function fn. That means whatever the resources that fn will take, whatever the resources fn take, if fn is representing the function for the growth of an algorithm, then whatever the function fn takes, and that will be its growth is less than the growth of gn, and gn provides an upper bound of to fn, and in that case we say fn is equal to big O of gn. But actually real notation is fn belongs to big O of gn. Here we are mentioning equal to gn, fn is equal to big O of gn, but in reality the thing is that fn belongs to big O of gn, because fn is a function and many functions may be bounded by gn. Hence big O of gn is a set where fn is a member, and fn belongs to big O of gn, but we in many books it is written as fn is equal to big O of gn. And this notation, this way of representation, if this condition is satisfied, then we say that gn gives upper bound to fn. Now let us take an examples. Is 17n square minus 5 is equal to big O of n square. Now for that, in order to prove it, we have to find a c and we find n0, and we will prove that that fn, which is equal to 17n square minus 5, is equal to big O of n square. Here gn is equal to n square. Now 17n square minus 5 is less than or equal to 17n square. Okay, hence here c becomes 17 and n0 becomes 1. Hence this condition for c is equal to 17 and n0 is equal to 1. Hence n beyond the value of n0 is equal to 1, and for c is equal to 17, this 17n square minus 5 is always less than or equal to 17n square. For whatever the value of n is equal to 1 or 2 or 3 or more than that. That means n value is greater than or equal to 1. Hence this function 17n square minus 5 is equal to big O of n square. Now consider another example, 35n cube plus 100 is equal to big O of n cube. And in that case also we have to find and c and n0, for which the condition fn is equal to 35n cube plus 100 is less than or equal to c of gn. Here gn is equal to n cube. Now hence for this 35n cube plus 100 is less than or equal to 36n cube. Hence in that case c is equal to 36, n0 is equal to 5. Hence for all n greater than or equal to 5, this condition is satisfying. Hence your 35n cube plus 100 is equal to big O of n cube. We are writing actually big O of n cube, but in reality it belongs to big O of n cube. Big O of n cube is a set, and 35n cube plus 100 is a function. And similarly 6 into 2 to the n plus n square is equal to big O of 2 to the n. In the similar way, we can find that this is 2 to 6 into 2 to the n plus n square is also equal to big O of 2 to the n, and in that case c is equal to 5 and n0. Sorry, c is equal to 7 and n0 is equal to 5. Now you see there are some complex classes. Why we are saying complex classes? We will discuss it later. These are some of the complex classes where n is in the x-axis and the function fn is equal to in the y-axis. Now the below one is the log n. Now the growth of log n is less than the growth of n, which is n is the linear time. Growth of n is less than the growth of n log n. Now growth of n log n is less than growth of n square. Growth of n square is less than the growth of n cube. Growth of n cube less than growth of 2 to the power n, and growth of 2 to the power n is less than growth of n factorial. N factorial. That means n is give upper bound to log n. N log n is upper bound to n square is upper bound to n log n cube is upper bound to n square, 2 to the power n is upper bound to n cube, and n factorial is upper bound to 2 to the power n. See, these are some growth functions. These are some growth functions. Now, why in the slide, why it is complex classes? See, log n is a function, a particular function. See, there are some algorithms or some functions who are coming, whose growth is same as your log n. Hence, all the functions whose growth is same as the growth of log n, they come under one class, and that and they are of same complexity, and that's why the functions which are coming under one class having same complexity is called complexity classes. Hence, log n is one complexity classes. All the algorithms whose growth is in the order of log n, they are in one class. All algorithms whose growth is of order n, they are comes under another class. Hence, they are the complexity classes. And remember that log n, n log n square, and n cube, all these, they are in polynomial. They are polynomial. You see, they are polynomial time, because and they can be these the functions or the algorithm whose growth is of this polynomial time are easily solvable by the computer, and they are called tractable. But the time, the complex classes n factorial and 2 to the n, they are not polynomial time, they are exponential in time. They are exponential time, and these type of algorithm or functions whose complex classes is 2 to the n or n factorial, they are called hard or intractable problems. Now, whether you suppose there is a problem and you want to write you have written a problem, then you can write the algorithm or a solution of the problem in different ways. Then, as I have already told, in case of analysis, that means your algorithm has to be compared with the other algorithms. In that case, you have to say that my algorithm is good or bad. Now, here I am taking an example where you will see that for a particular problem, the solution or the algorithm is written in 3 ways, and we will see how the time complexity of this algorithm is we are calculating, and we will say that which algorithm is better in terms of time complexity. See, in this example, suppose a number is given, a n-bit number is given, and we want to count in that n-bit number how many ones are there, counting the number of ones of a n-bit string, n-bit number. Now, in this case, what happened? Simply we can see that c is equal to 0 in this solution 1, c is equal to 0. For I is equal to 1 to n is the number of bits. And if bi is equal to 1, if the particular bit is bit is 1, then c will be c1. Hence, in that case, what happens? The for loop will run how many times? N times. The for loop will run n times, and you will check whether particular bit I is 1 or not. In that case, the count will be increased. Hence, the time complexity, it depends on the for loop which is runs on what is n times, and the time complexity n of this program code or of the algorithm which uses this logic is we go for n. But consider the another way of solving it. Assuming that we have the n-bit string which is equal to bn to b1. Now what happened? The algorithm is used here, make c is equal to 0, and the algorithm is equal to while b is not equal to 0, because in this case b is changing. In that case, previous one case b was not changing. In this case b was changing. While b is not equal to 0, c is equal to c plus 1, and a new b will be old b logical and of old b minus 1. New b is equal to old b logical and of old b minus 1. And in this case, the algorithm is and new b is updated, and it will check whether it is equal to 0 or not. If it is not equal to 0, then C will be C plus 1, and hence it will count whether it is counting the number of ones or not. That we are using this algorithm, whether it is possible or not to easily calculate the number of ones of the bit string of the number B is given. Now you see, suppose in the example B is equal to 1, 000, 1. Suppose this is the value of B where you want to calculate the number of ones. And the answer is 3, as you see. But how this algorithm is calculated, that we are seeing. Say in that case, C is equal to 0. Now first of all, it will enter into the loop B is not equal to 0, because B is equal to 1, 000, 1. Hence B is not equal to 0. Hence C will be 1. Now the new B will be the old B, that is 1, 000, 1. Logical AND of B minus 1, that is 1, 000, 10. B minus 1. Hence, if you do the logical one, the new B will be B dash, which is equal to 1, 000, 10. Now, this new B is not equal to 0, hence C will be 2. And it's again, it will be logical AND of C minus 1, that means B dash minus 1, that means 1, 401. And since logical 1, your new B will be 1, 50, and the new B is not equal to 0, hence C will be 3. Now, new B will be logical AND of the new B minus 1. Now what will happen if you do this? Now the final B will be 0, hence the final B is not equal to 0, the condition is not satisfying, hence it will be out of the loop. At that time C will be 3. Hence this logic is calculating exactly how many number of ones in the initially we have given. Hence in this case, the time complexity, the loop will not run n times as in case of a previous one. Rather it will run how many number of ones, that times you see how many number of ones. See, C is 3, the number of ones 3, hence C1 is 1, 2, 3. 3 times it is running. Hence in this case, time complexity of Tn is big of number of ones. You see, for the same problem, the way of designing the algorithm, the time complexity is also changing. Hence, it is very much essential for any kind of problem. It is very much essential to design a better algorithm for solving the problem. Now, the question is that whether this is a better algorithm or is there any algorithm which is not better than that to solve this problem? Let us come to the third way of solving it. The third, though I am not discussing the algorithm, but rather I am saying, suppose this is the B, then take all the odd position digit and take all the even position digit and add it. Now B is given, take all the odd position digit and take all the even position digit, then add it. Now doing this, this becomes in the second column, sorry, second row. Then again it is not finished. Take all the odd position digit and take all the even position digit, then you add it, and again you do it. Now finally, if that is not possible to divide in odd position and even position, your loop will terminate. Now you see, this in this case the loop will terminate because that is not possible to divide as it is previously. Hence here the value of B is 3. Is 0, 1, 0, 0. The value of B is 3. Hence this is the, if some algorithm uses this kind of logic, then it will take log n time. The order of the algorithm which uses this logic, then it will take log n time. We will calculate how it will be log n in later class. You will understand how the time complexity of this kind of logic will take log n time. That will calculate later. But if, for the timing, you remember that if some algorithm uses this logic, the time complexity will be big of log n time. That means for solving the same problem, we have developed 3 algorithms. One is taking big of n times, one is taking big of number of ones, and another is taking big of log n times. My point is that in this case, what happens, depending on the way of designing the algorithm, the same problem can be solved in a better way. Hence, designing and analysis of the algorithm is essential for solving any kind of a problem in the computer. Okay, any kind of problem in the computer. Now, we are discussing about Bagwan notation, and in that case, how this is to solving the same problem with 3 different ways. The time complexity Bagwan they are varying, and hence it is essential to design analysis in a proper way. Now, another is the omega notation. See, omega notation means it is gives the lower bound. Omega notation is nothing but it gives the lower bound for a particular algorithm or a growth of a function. Suppose fn is a function, we say fn is equal to omega of gn if there exist two positive constants c and n0 such that the value of fn is always greater than the value of c of gn, value of c into gn for all n greater than equal to n0, for all n greater than equal to n0. Then in that case we say that gn provides the lower bound of to fn. Gn provides the lower bound of fn. You see in this case, in the growth of fn is there, the growth of c into gn is there. Now at a particular value of n is equal to n0, beyond that f of n is always greater than equal to c of gn. If this condition is satisfying, then we will say that gn provides lower bound of fn, and we will say that fn is equal to omega of gn. Actually we have to write in the real notation is fn is belongs to omega of gn, because omega of gn is a class and fn is a member of that class, that complexity class. Okay, now hence this is the omega notation. Let us take some example. 3n plus 2 is equal to omega n. Okay, 3n plus 2 is greater than 3 into n for all n greater than equal to n. Hence in that case c is equal to 3 and n0 is equal to 1. See, 3n plus 2 is greater than equal to 3n for all n greater than equal to 1. Hence here n0 is equal to 1 and c is equal to 3. Hence 3n plus 2 is equal to omega of n. Similarly, you see, is 3n plus 2 is omega is equal to 1? Yes, you can see 3n plus 2 is greater than equal to 1 into 1 for all n greater than equal to 1. Hence here c is equal to 1 and n is equal to 1. Hence 3n plus 2 is omega of 1. Now in this case 6 into the n plus n square is equal to omega of n, but in that case we never find you see 6 into the n plus n square is omega of n to. Okay, for that we can find also, and we can say that 6 into the n plus n square is equal to omega of n by n to the power 100, because n to the power 100 is a polynomial but it is a exponential. It will be lower bound, it provides a lower bound. Hence another growth function is we are considering is theta notation, and theta notation here you write them. Theta notation provides the tight bound. As we have told, one is giving upper bound and here it is giving upper bound and lower bound. Now in this tight bound means a function fn is said to be tight bound or a theta of gn if there exist three positive constants. Remember, three positive constants c1, c2 and n0 such that c1 in the value of c1 into gn is less than the value of fn is less than the value of c2 into gn. That means in this case value of fn is is smaller than the value of c1 gn and bigger than the value of c1 gn and the smaller than the value of c2 gn. That you see in the illustrating that fn is in between the c1 gn and c2 gn for a particular value of n greater than n0. If this is the condition is satisfying, then in that case we say that gn provides tight bind to fn. That means fn belongs to or fn is equal to theta of gn. Fn belongs to or fn is equal to theta of gn. That means theta of gn, that means it is the theta notation provides to any function provides the tight bound. Tight bounds, the same function is gives the upper bound and also same function gives the lower bound. If the same function gives the upper bound and same function gives the lower bound, then the function gives the tight bound to a particular function. Now let us consider 3n plus 2 is equal to theta n. Yes, you can say that 3n is equal to 3n plus 2 is less than equal to 4n and is greater than equal to 3n. Hence in that case c1 is equal to 3, c2 is equal to 4 and n0 is equal to 2. Hence 3n plus 2 is equal to theta of n. Similarly, is 3n plus 2 is equal to theta of n square? No, it is not the case. because a n square cannot provide the lower bound to 3n plus 2. It can provide the upper bound, but it cannot provide to the lower bound. N square cannot give lower bound to 3n plus 2, because 3n plus 2 always takes less than n square. Okay, hence n square never provide lower bound. Hence 3n plus 2 is not equal to omega of n square. Hence it is not equal to 3n plus 2 is not equal to theta of n square. Similarly, 6 into 2 to the power n plus n square is equal to theta of 2 to the n. Yes, you can find this, and hence it is provided for a particular value. For C1 is equal to 6, C2 is equal to 7, and n is equal to 4, the condition is satisfied. That means 6 into 2 to the n is less than equal to 6 into 2 to the n plus n square is less than equal to 7 into 2 to the power n. Hence, 6 into 2 to the n plus n square is equal to theta of 2 to the power n. And is 4 to the n cube plus 3n square is equal to theta of n square? No. N square cannot provide upper bound to n cube. N square growth function is not provide upper bound to the n cube function. Hence, this cannot provide upper bound. Hence, it can never provide tight bound. That means if a function provides tight bound, means it has to provide the upper bound and also it has to provide the lower bound. But in this case, n square never provides upper bound to n cube function. Hence, it cannot provide the tight bound. N square function gives the lower bound to n cube function, but it cannot provide upper bound to n cube function. Hence, it cannot provide tight bound. Hence, properties are of order, that the order function is transitive. That means if Fn is big of Gn and Gn is big of Hn, then Fn is big of Hn. If Fn is, second one is Fn is equal to omega of Gn and Gn is omega of Hn, then Fn is omega of Hn. If Fn is equal to theta of Gn and Gn is equal to theta of Hn, then Fn is equal to theta of Hn. That means the order functions follow the transitive, and the order function follow the reflexive. That means Fn is equal to big O of Fn. Any function also gives the upper bound to itself. Any function also provides the lower bound to itself. Any function also provides the tight bound to itself. This is the reflexive. Now, symmetric. If Fn is equal to theta of Gn, if and only if Gn is equal to theta of Fn. If a function Gn provides tight bound to Fn, then Fn also provides tight bound to Gn. And another symmetric is if Fn is equal to big O of Gn, then Gn is equal to omega of Fn. If and only if Gn is equal to omega of Fn. These are the two rules for symmetric. Okay. Now we are ending the class asymptotic notation.